11 days. That's how long a payment validation silently dropped edge case transactions in a live e-commerce system before anyone noticed. No alerts fired. No tests failed. The code was clean, well commented, and it was written entirely by an AI coding assistant. I was the senior engineer called in on day 12. The dev who shipped it wasn't incompetent. He was experienced, careful, and he'd reviewed the code. The problem wasn't developer. The problem was that AI-generated code carries a kind of false authority. It looks like it was written by someone who knows exactly what they're doing. And that's the trap. Normal developer skepticism, that little voice that says, wait, does this handle the null case? Gets switched off, because surely the AI already thought of that. Right, wrong. By the end of this lecture, you will have a 2-layer checklist that would have caught this bug before it ever touched production. Here's what makes AI-generated code uniquely dangerous compared to code a junior developer writes. When a junior writes something off, you feel it. The naming is inconsistent, the structure is a little awkward, something smells wrong, and your brain flags it for closer inspection. AI-generated code doesn't smell wrong. It smells professional. It uses your project's naming conventions, it adds doc strings, it handles the path elegantly. Your brain pattern matches it against competent senior engineer output and moves on. This is what I call the authoritative mediocrity trap. The code is mediocre in the ways that matter: edge case coverage, domain-specific business rule awareness, long-term maintainability. But it presents itself with the confidence and surface polish of expert work. And here's the brutal part. The more experienced you are, the faster you skim. Senior engineers are actually more vulnerable to this trap, not less. But wait, there's a specific structural reason why AI code fails in a predictable pattern, and that's exactly what we'll dissect next. Let's talk scale, because this isn't just one team's war story. According to GitHub's 2023 developer survey, over 92% of US-based developers are now using AI coding tools in some capacity. Stack Overflow's data puts enterprise adoption above 70% for teams over 50 engineers. Now look at the other column, documented AI code-related production incidents. A 2024 analysis, Gartner flagged that fewer than 5% of enterprise teams have any formal AI code review gate in their deployment pipeline. That means the overwhelming majority of teams are shipping AI-generated code with the same review process they use for human-written code, which, as we just established, is exactly the wrong approach. The gap between adoption and safety infrastructure is not a small gap. It's a canyon, and the teams falling into it aren't reckless, they're just moving fast without a map. In the next section, I'm going to give you that map, starting with the specific checklist framework that closes this gap. So what are you actually walking away with from this lecture? Not theory. Not vague warnings about being careful with AI. A concrete, 2-layer audit framework. Here's how it's structured. Layer 1 is Anthropic's official safety recommendations, the guidelines their own researchers published for production use of Claude-generated code. Most teams have never read this document. We're going to extract the operationally useful parts and turn them into a checklist you can run in a CI pipeline. Layer 2 is the field-tested overlay, 25 years of enterprise deployments, Korean SI project patterns, and the specific failure modes I've personally seen in financial, logistics, and government systems. These are the gaps that Anthropic's general guidelines don't cover, because they can't know your regulatory context and your legacy integration surface. The combination of these 2 layers is what I call the dual verification structure. Each item in the checklist has a source, either the Anthropic guideline it maps to, or the production incident that generated it. No item is there without a reason. Surprised by how few teams know about Anthropic's official guidance? That's exactly what we dig into in Chapter 2. Before we go deeper, let me be direct about who this lecture is for. Because the right answer for a 5-person startup is not the same as the right answer for a 500-person enterprise team. If you're a startup CTO, your focus is Chapters 2 and 3. The 5 failure patterns and the minimum viable safety gate you can implement in a single sprint without slowing down your velocity. If you're a tech lead at a mid-sized company, Chapters 3 through 5 are your target zone. That's where we cover code review process redesign, team training patterns, and how to have the AI code policy conversation with your engineering org. If you're an enterprise architect or CISO dealing with regulated industries, financial services, healthcare, government, Chapter 6 is built specifically for you. Compliance mapping, audit trail requirements, and the contractual liability questions your legal team is already asking. Every chapter builds on the previous one, but you can also use this as a reference, jump directly to your context. And here's what I want you to carry into the next chapter. The 5 failure patterns we're about to cover aren't random. They follow a structural logic rooted in how large language models actually work, and once you see that logic, you will never review AI-generated code the same way again. Let me be direct about something most AI tutorials won't tell you. When an LLM writes code, It is not executing logic. It is predicting the next most statistically probable token. That distinction sounds academic until your payment service calls a deprecated Stripe API that no longer exists, and the AI generated it with perfect confidence and zero error. I've seen this exact failure in production. The model's training data had a cutoff. Stripe updated their SDK, but the LLM never knew. The generated code looked immaculate, clean formatting, correct variable names, even inline comments. Nobody caught it in review because it looked more complete than what a junior dev would write. That is the core danger. Plausible, but wrong code is invisible until it detonates. And here's what makes this worse than any bug a human writes. A human dev who doesn't know something leave a todo comment, throw a placeholder error. An LLM fills that gap with confident fiction. By the end of this chapter, you will have a named taxonomy for every class of this failure, and a scoring system to prioritize which ones to block first. Now here's the second failure mode, and this one trips up even senior engineers who should know better. When you paste a function into ChatGPT or Claude and ask it to fix a bug, the AI sees that function, and only that function. It has no idea that your database connection pool is initialized in a singleton 3 files away. It doesn't know that the user service has a custom retry decorator applied at the class level. It doesn't know your middleware already validates the JWT before this function ever executes. So it generates perfectly reasonable-looking defensive code, redundant null checks, duplicate auth logic, connection objects created inline that don't just waste resources, they actively conflict with what the rest of your system is doing. I had a team in a fintech project where AI-generated code opened a second DB connection inside a transaction that was already managed by a connection pool. Unit tests, all green. Load tests at 500 concurrent users. The context window is not your codebase. That gap is where integration bugs are born. And here's the uncomfortable truth. This problem gets worse, not better, as your codebase grows. The third failure mode is the most psychologically uncomfortable one to admit, because it's about us, not the AI. When a human colleague submits a 50-line pull request, you read it carefully. You question the logic. You ask why they chose that approach. But when an AI generates 200 lines of well-structured, well-commented code with a clean architecture, research shows review scrutiny drops dramatically. The output looks authoritative. The formatting is perfect. There are no spelling mistakes that trigger your junior dev alert. Your brain pattern matches to this looks like senior-level code, and your review depth decreases accordingly. I call this cognitive offloading. You unconsciously delegate your judgment to the tool. In one study from Stanford, developers spent 30% less time reviewing AI-generated code than equivalent human-written code of the same complexity. That's INIS. That's a predictable cognitive response to apparent completeness. The danger isn't that developers trust AI blindly. The danger is that they trust it slightly too much, consistently, at scale, across every pull request. And that consistent 30% gap is exactly where all 5 failure patterns I'm about to show you will hide. Alright, let's name these failures specifically because vague warnings don't save production systems. Pattern 1 is security injection. When you ask an AI to generate a database query function, it will frequently, not occasionally, frequently, construct SQL strings by direct interpolation. I've audited over 40 enterprise codebases where AI-assisted code was introduced in the past 2 years, and SQL injection appeared in roughly 1 in 5 data access functions. The AI isn't being careless. It's pattern matching to the simplest working example from its training data, which often predates parameterized query adoption in those frameworks. Pattern 2 is silent exception swallowing. Ask any AI to handle errors gracefully, and you'll get a beautiful try-catch block that catches exception, logs nothing, and returns null. I have seen this exact pattern in payment processing code. A third-party API timeout gets swallowed, the function returns null, and upstream code interprets null as transaction successful. The transaction never happened. The customer got charged. This is not a hypothetical. This is a postmortem I wrote. These 2 patterns alone cover the majority of critical severity findings in AI code audits I've conducted. Look at this table carefully. Pattern 3 is the one that kills you slowly, async and concurrency mishandling. This is especially dangerous. It is nearly impossible to reproduce in a development environment. Look at this code. An AI generated this async function to update a user's wallet balance. It looks correct. Await on the database read, calculation done, await on the write. What it doesn't account for is that 2 requests can enter this function simultaneously, both read the same starting balance of 1,000, both calculate independently, and both write back. One writes 900, the other writes 800. You lost 100 units of currency due to a race condition with no error, no exception, no log entry. Everything appears to have worked, in a test with 1 request at a time, perfect. In production with 200 concurrent users during a flash sale, Silent data corruption. I've seen this exact scenario in a Korean e-commerce platform. They discovered the bug 3 weeks after launch by reconciling their payment processor records against their DB. They were off by 4.7 million won. The fix is a database-level lock, or an optimistic concurrency check with a version field. The AI almost never generates either of these by default, unless you explicitly describe your concurrency requirements in the prompt. Most developers don't, and here's what that means for your review process. I'll show you the detection strategy in the next section. Pattern 4, credential hardcoding. This one seems obvious, and yet in my audits, I find it consistently in AI-generated code, especially in configuration helpers, test setup files, and database seeds. The AI is optimizing for a working example. A working example needs a real-looking value. So it generates API key I prod AB1 tornxes or dwasword 2 and the developer merges it without stripping it out, because everything else in the fine and they were moving fast. That value is now in your Git history forever, even if you delete it in the next commit. If your repo is private today and public tomorrow, or if an internal employee extracts it, you have a breach. Pattern 5 is what I call scope creep functions. The AI is asked to write a helper function to format user data for the API response. It generates that function, and also adds a convenience method that writes directly to the database, another that reads from an internal config file, and a utility that accepts a raw SQL string as a parameter. None of these were asked for. All of them expand the attack surface. The function quietly exceeds its intended permission boundary, and because it works, nobody removes the extra methods. Use this checklist before merging any AI-generated utility function. Every item on this list is a gate, not a suggestion. Now that you have all 5 patterns named, the next question a tech lead always asks me is, where do I start? You can't gang every day one, your team will revolt and the AI tooling adoption dies. So you need a prioritization framework. I use a frequency versus impact matrix, and after auditing dozens of code bases, the positions of these 5 patterns are consistent enough to be prescriptive. Security injection sits in the top right corner, high frequency, critical impact. This is your first gate, no exceptions. Silent exception swallowing is high frequency but variable impact. In a payment system it's critical, in a read-only reporting service it's high. Context matters. Async race conditions are lower frequency, they require specific concurrency scenarios. But when they hit, they produce silent data corruption that can take weeks to detect, making impact catastrophically high. Credential hardcoding is medium frequency, critical impact. One hit can be a breach. Scope creep is the highest frequency of all 5 but lowest immediate impact. It's a slow security debt accumulation, rather than an acute incident. This matrix tells you, block patterns 1 and 4 first with automated scanning, escalate pattern 3 to mandatory architecture review, and handle patterns 2 and 5 through code review checklists. Does your team's production environment shift any of these positions? Ask yourself that question before the next scene. Let's close this chapter with the question that determines everything about how you operationalize this knowledge. Which of these 5 patterns can a machine catch, and which ones require a human brain? This distinction is not academic. It determines your tooling budget, your review process design, and honestly, whether your developers will process at all. Pattern 1, security injection, largely automatable. SimGrep, SonarQube, and GitHub Advanced Security all have rules for this. You can gate it in CI in 1 afternoon. Pattern 4, credential hardcoding, completely automatable. Git secrets, Trufflehog detects secrets. No excuse for not having this running today. Pattern 2, silent exception swallowing, partially automatable. Static analysis can catch all blocks with empty bodies, context-aware silent failures need human judgment. Pattern 3, async race conditions, not automatable in any meaningful way. Thread sanitizers help but produce too many false positives for CI gating. This requires a senior engineer who understands your specific concurrency model. Pattern 5, scope creep, not automatable, requires understanding what the function was supposed to do versus what it actually does. That's a human judgment call every time. Here's why this matters for the next chapter. Anthropic's official guidelines address exactly this tooling versus human review boundary, and what their research recommends will probably surprise you. The answer is not what most teams implement. Let's get one thing straight before we go any further. When developers quote Anthropic's guidelines in Slack channels, they almost always get it wrong. I've seen tech leads cite Anthropic says AI code is production ready, and I've traced that claim back to a blog post that says the exact opposite. Anthropic's responsible scaling policy and their model cards are very specific. Claude and similar models, tools that require structured human oversight, not autonomous agents you deploy and forget. The official framework has 3 pillars: capability evaluation, deployment context assessment, and mandatory human review loops. None of these are optional. None of these say trust the output. What Anthropic actually publishes is a safety-first constraint model, not a green light for autonomous code deployment. The gap between what the research says and what your team believes it says, that gap is where production incidents are born. And in the next scene, I'll show you exactly where the human authority boundary is drawn. Now let's talk about the human-in-the-loop principle. Because this term gets thrown around like means someone glanced at the diff. It doesn't. Anthropic's usage model documentation defines a review gate as a point where a qualified human can reject, modify, or remove an AI output before it crosses an irreversible boundary. The key word is irreversible. Committing to main is a gate. Merging a PR is a gate. Deploying to production is a gate. Calling a third-party API that charges money or modifies customer data, that is a gate. What is an AI gate? A developer 400 lines of AI-generated code in 2 minutes while eating lunch. The accountability chain runs like this. The AI author generates, the human reviewer owns the output the moment they approve it, and the security lead owns the blast radius if the review was inadequate. This is not bureaucracy. This is how you keep your name off the incident post-mortem. But here is where it gets uncomfortable. Most teams have no formal definition of where AI authority ends. I'll show you what missing boundary costs you. The third pillar in Anthropic's framework is output verification, and this is where the guidance gets technical enough that most teams stop reading. Anthropic recommends a layered validation architecture, not a single code review. Think of it as a stack. At the top, you have static analysis, linters, SaaS tools, dependency scanners running automatically on every AI-generated file. In the middle layer, you have semantic verification. Does this code actually do what the prompt asked? This requires a human or a secondary AI pass with a different context window. At the base, you have integration validation. Does this code behave correctly when connected to your actual production data models, not mock data? The failure pattern I've seen 100 times is teams that implement the top layer only and call it compliant. Static analysis catches syntax problems. It does not catch logic bombs. It does not catch business rule violations, and it absolutely does not catch the kind of subtle data exposure bug that passes every linter and fails every security audit 18 months later. The stack only works when all 3 layers are active. Coming up next, I'll show you how to map this stack onto your actual CI/CD pipeline as a stage gate model. Alright, let's make this actionable. Anthropic's checklist is abstract by design. It's a research framework, not an engineering runbook. My job for the last 25 years has been translating abstract frameworks into things that actually rings. So here's the translation. You map the Anthropic checklist onto 3 gate points in your CI/CD pipeline. Pre-commit, pre-merge. Commit is the fastest gate. It runs in under 30 seconds, it's fully automated, and it catches the obvious problems before they pollute the shared branch. Pre-merge is the quality gate. This is where human review is not optional. This is where the semantic verification layer I just described actually runs. And this is where your security lead has sign-off authority. Pre-deploy is the final gate. Integration validation, environment parity check, and the go-no-go decision that carries real organizational accountability. Here is the critical insight most teams miss. If you put everything in the pre-deploy gate, you're doing expensive validation on code that's already been trusted by 2 teams. Shift left. The pre-commit gate should be brutal, so the pre-deploy gate is boring. But wait, not every item on this checklist can be automated, and that distinction matters enormously. Now let's split each gate into what can be automated versus what must have a human signature. This distinction is not philosophical. It's a compliance requirement in any audited environment. Automated items at pre-commit. SAST scan pass, no hard-coded secrets detected, all dependencies pinned with known CVE status, file size anomaly check for suspiciously large AI-generated files. At pre-merge, automated items include test coverage threshold met and no regression in integration tests. But here is where you must stop and get a human architecture impact assessment. Has this AI-generated code silently violated a data model boundary or introduced a circular dependency the linter cannot see? That requires a senior engineer. Ownership assignment. Who is the named human responsible for this code block in the next incident? That requires a decision, not a scan. And at pre-deploy, the security lead must physically sign off on any AI-generated code touching authentication, authorization, payment flows, or piece handling. Not a bot. Not an approval workflow with a 2-second timeout. A named human who read the code and can defend the decision in a post-mortem. Anti-pattern I've seen too many times. The entire checklist is automated, including items that require judgment. The pipeline goes green, and everyone assumes safety. That is exactly how you end up in the next chapter's failure reconstructions. Every team eventually faces this moment. It's 2 in the morning, the CEO is calling, and someone wants to bypass the gate. Let me tell you, gate bypasses happen. They will happen on your team. The question is whether the bypass is controlled or chaotic. A controlled bypass has 3 mandatory components. First, a named approver with authority level documented, not the on-call engineer, but a specific named individual with director level or above authorization. Second, a time-bounded compensating control. The bypass checks must be executed within a defined window, typically within 4 hours of deployment, and the results must be committed to the audit trail. Third, an automatic rollback trigger. If the compensating controls find a problem, the rollback procedure must be pre-authorized and pre-staged before the bypass is approved. The anti-pattern is the "we'll check it later" bypass where later never arrives. I've watched teams bypass gates under pressure, ship a fix, and then spend 6 months with a security vulnerability quietly living in production because the compensating review never happened. The bypass itself is not the failure, the absent audit trail is. Heading into the next section, we'll expose the 3 areas the Anthropic guidelines don't cover at all. And that silence is exactly where enterprise teams get blindsided. Here is what nobody tells you when they hand you Anthropic's guidelines and say follow these and you'll be fine. The guidelines were written by researchers operating in a greenfield, cloud-native, English-language software context. They are excellent within that context, but there are 3 entire categories of risk that the guidelines do not address. And these 3 categories describe the majority of enterprise production environments in Korea and across Asia-Pacific SI ecosystems. First, legacy system integration. When AI-generated code must interface with a COBOL batch system from 1987 or a homegrown ERP with undocumented side effects, the Anthropic framework has nothing to say. The validation assumptions break entirely. Second, SI vendor code handoff. In Korean enterprise environments, AI-generated code frequently crosses organizational boundaries. Your development team generates it, an SI vendor integrates it, and a separate operations team owns it in production. The accountability chain the guidelines describe assumes a single organization. It does not survive a handoff. Third, enterprise compliance audit trails. Financial regulators, healthcare auditors, and government procurement standards require documentation that AI-generated code simply does not produce by default. The guidelines mention audit trails, but provide no structure for regulated industry requirements. These gaps are not failures of the research, they are gaps between research context and production reality. And the next scene is where I show you what to do about them. So what do you do with 3 gaps that the official framework doesn't cover? You extend it. Over 25 years of production operations, systems, ranging from first-generation internet banking platforms to modern microservice architectures, I've built what I call the field validation layer. It sits on top of the Anthropic framework and fills each gap with a concrete check that can actually be enforced in an enterprise CI/CD pipeline. For legacy integration gaps, every AI-generated interface must be accompanied by an explicit integration contract document listing all assumed behaviors of the downstream legacy system, signed by the engineer who owns that system. No document, no merge. For SI handoff gaps, AI-generated code packages must include a handoff manifest, model name, version, prompt hash, generation timestamp, and the name of the human who reviewed it. That manifest travels with the code through every organizational boundary. For compliance audit gaps, every AI-generated file must carry a structured header, comment in machine-readable format specifying AI involvement level, review type, and reviewer identity. This becomes the raw input for your compliance report. These 3 additions are not theoretical. They are running in production pipelines right now. And in the next chapter, you'll see exactly what happens when teams skip them. 3 real failure reconstructions, names changed but code intact. Let's start with the one that kept a fintech team awake for 3 weeks, and they didn't even know it was happening. An AI-generated currency rounding function passed every single unit test. Code review approved it in 15 minutes. It looked clean, idiomatic, modern. And then, over 23 days, it silently accumulated floating point drift in the transaction ledger. Not one alert. Not one exception was thrown. The discrepancies were subcent per subcent until they weren't. By day 23, the ledger was off by thousands of dollars across millions of rows. The AI wrote code that was correct for general-purpose math, but catastrophically wrong for financial domain math. Here's the exact timeline of how a green build turned into a regulatory incident, and the answer will change how you review every financial calculation going forward. Here is the actual code pattern that caused the failure. Look at this carefully, because on the surface, it looks completely reasonable. The AI generated a standard JavaScript floating point rounding approach using toFixed and parsefloat. This is perfectly fine for a UI display label. It is a financial disaster for ledger persistence. The problem is that parsefloat reintroduces floating point representation error after to-fixed stringifies it. The correct approach for financial calculations in any language is integer-based arithmetic. Store amounts as cents as integer types, never as floats, and only convert at the display layer. No AI model, including the best ones available today, consistently applies this domain rule without being explicitly prompted. The AI learned from millions of general-purpose JavaScript examples. Financial precision and variance are not in the general corpus. That gap is your responsibility as the reviewer, not the AI's. But wait, this wasn't the only gap. The test suite had 47 tests and 0 of them covered accumulated precision over sequential operations. So what does this case permanently add to our master checklist? One non-negotiable rule: domain-specific invariant verification. This is the class of bugs that automated tests will never catch unless someone who knows the domain wrote the tests. AI models generate statistically likely code. For financial systems, statistically likely means correct for web apps, not correct for money. Your checklist must include a mandatory domain expert sign-off for any AI-generated code touching currency, tax, interest, or regulatory calculations. Not a code review, a domain invariant review. Ask one question: does this code make assumptions that are true in general programming but false in this specific financial domain? In this case, the assumption was that floating point is fine for intermediate calculations. That assumption cost 3 weeks of remediation and an emergency audit response. The next case is worse, because the window was exploitable in real time. But case 2 is the one that makes security engineers go quiet in the room. An e-commerce platform asked an AI to generate JWT token refresh logic. The generated code was architecturally sound. The logic for validating the incoming token was correct. The logic for issuing a new token was correct. But in between, in the transition state during token rotation, the AI created a 40-second window where a user's role claims were not revalidated against the current database state. They were carried forward from the expiring token. An attacker who timed a request to land in that window could escalate from a standard customer role to a seller admin role. This was not a theoretical vulnerability. It was exploitable. And it sat in production for 6 weeks undetected because every security test in their pipeline tested authentication, not the race condition in the rotation handoff. This is the class of vulnerability that no static analysis catches because the code is individually correct. The danger in the sequence. Let me show you exactly where the vulnerability lived in the token lifecycle, because this is what a security-focused review gate would have caught and what a standard code review missed entirely. The flow has 4 states: the active token, the refresh request received, the new token issued, and the old token invalidated. Standard code review checks that steps 1 and 4 are correct. The AI implemented both correctly. What it did not do is atomically bind the role revalidation to the issuance of the new token. There is a gap between receiving the refresh request and completing the database role lookup, and during that gap, the old token's role claims are in a trust limbo. The AI cached the claims object from the incoming token and passed it forward as a performance optimization. This pattern is documented in dozens of JWT tutorials. It is also the exact pattern that creates escalation windows. The question a security gate asks is not "is this code correct?" It asks what is the trust state of every claim at every point in this sequence. The checklist rule this case adds is mandatory and non-negotiable. Any AI-generated code that touches authentication, authorization, session management, or token lifecycle requires a dedicated security lead sign-off, not as part of the standard pull request review, but as a separate gate with a defined attack surface checklist. The reviewer must answer 3 questions explicitly. 1. What is the trust state of every security-relevant claim at every state transition? 2. Is there any window, however brief, where claims are assumed rather than verified? 3. Does any performance optimization in this code defer or cache a security verification? If the answer to any of those is "I'm not sure," the code does not ship. AI models are trained on documentation and tutorials. Security tutorials now prioritize clarity over defense in depth. The AI did exactly what the tutorials taught it. Your security gate has to be smarter than the tutorials. Now, the third case will make you rethink how you run infrastructure automation entirely. The third case is the one I use to end arguments about whether AI can handle infrastructure code. A team asked an AI to generate a Terraform cleanup script to decommission staging resources after a feature freeze. The AI did exactly what was asked. It identified all resources matching the target naming pattern, staging, pyo, and generated correct Terraform destroy blocks for every one of them. Problem: 6 months earlier, a production database had been renamed during a cost optimization refactor. Its new name started with staging dprod, a legacy naming artifact that nobody had updated in the resource registry. The AI had no way to know this. The script was syntactically perfect. The plan output looked reasonable to the engineer, who ran it without a dry run review. The apply command deleted 3 production database instances in 47 seconds. Backups existed, but the recovery took 11 hours and cost 2 engineers a full weekend. The AI did not make a mistake, the process made a mistake. And the process had 3 specific gaps that a proper ISC gate for AI-generated code would have closed. Let me show you the gap between this team's existing ISC review process and what an AI code-specific ISC gate actually requires. Their existing process had 3 steps: generate the script, review the code, apply. That process is completely adequate for human-written infrastructure code, because a human engineer who wrote the script has a mental model of the environment. They know which resources are active. They know the naming history. The AI has none of that context. It has the prompt and the naming pattern you gave it. An AI-specific ISC gate needs 6 steps, not 3, and the 3 steps they skipped were labeled obvious in their internal runbook. Obvious steps are the ones that kill you. The mandatory additions are a resource inventory crossed against live state before the plan runs, a blast radius assessment that explicit lists every resource class that could match the targeting pattern, and a mandatory dry run review, not a glance at the plan output, but structured sign-off that easted resource has been confirmed as a non-production target. Let's close this chapter by consolidating what 3 real production failures have taught us. We now have a master checklist that layers Anthropic's official guidelines with 3 field-extracted rules that the research documents do not cover. Rule 1. From the fintech case, domain invariant gate, AI generates statistically likely code, not domain-correct code. Any financial, regulatory, or precision-sensitive calculation needs a domain expert sign-off that goes beyond code review. Rule 2. From the auth bypass. Security state audit. For any auth or authorization code, trust state every transition must be explicitly verified by a dedicated security reviewer, not bundled into PR review. Rule 3. From the Terraform incident. Blast radius assessment. For any AI-generated infrastructure code with destructive operations, a 6-step gate with mandatory dry run and structured sign-off is non-negotiable. These 3 rules are not any AI vendor's official documentation. They come from systems that failed in production. In the next chapter, we build the complete deployment roadmap, sized for your team, that operationalizes all of this into something your team can actually ship with. All right. After 3 brutal production failure reconstructions in the last chapter, you deserve something actionable. This is the moment we've been building toward, the complete, consolidated master checklist. Every gate we've discussed, automated checks, mandatory human review items, domain-specific rules for financial logic, auth systems, and data migration, they're all here in one place. This is not a theoretical framework. This is a battle-tested checklist I've refined across real deployments, cross-referenced against Anthropic's official safety guidance, and hardened with the specific failure patterns I've seen in Korean SI and enterprise environments. I'm making this available as a downloadable PDF. The link will be in the course materials. Print it. Put it on your wall. Make it part of your PR template. The teams that treat this as a living document rather than a one-time read are the ones that stop having AI-related incidents. But before you download it, let me walk you through what's actually in it. Because a checklist you don't understand is just checklist theater, and that's one of the anti-patterns we'll destroy later in this chapter. Now here's the uncomfortable truth about checklists. If you hand a 40-item checklist to a team that's never done structured AI review before, they will check every box in under 3 minutes and ship anyway. I've seen it. So we need to tier this. The minimum viable gate. 7 items that you can implement this week without a single organizational approval, without a security team, without budget, versus the progressive enhancement items that you layer in over the following months. The must-have tier is non-negotiable. These 7 items catch approximately 80% of the production failures we reconstructed in the previous chapter. The progressive items are what separate a team that's doing okay from a team that's genuinely production-hardened. The key insight here is that progressive adoption is not an excuse to stay at Tier 1 forever. Set a 90-day deadline. Teams that don't have a deadline for getting to full compliance never get there. I've watched that happen too many times. The question you should be asking right now is, which of these 7 must-have items does your current already cover? And which ones have zero enforcement today? The number 1 reason checklists fail isn't laziness. It's friction. If enforcing a gate requires a developer to manually run a script and paste the output into a PR comment, it will be skipped under deadline pressure. Every single time. So here's the concrete tooling map. Static analysis. You wire SendGrep into GitHub Actions with a YAML workflow that takes about 20 minutes to configure. For secret detection, detect secrets as a pre-commit means the check happens before the code even leaves the developer's machine. Zero CI cost. For dependency auditing, Snake's free tier covers most small teams and integrates directly into the PR as a status check. For human review enforcement, GitHub's code owners file plus required reviewers in branch protection rules means you cannot merge without the right person signing off. And that's a 2-minute repository setting. The architecture here is a stack. Developer machine at the bottom, CI pipeline in the middle, merge gate at the top. Each layer catches what slips through the one below. The goal is that no single point of human failure let dangerous AI code reach production. And here's the thing that will blow your mind in the next section. The roadmap for implementing this stack looks completely different depending on whether you're a 3-person startup or a 500-person enterprise. Let's talk about the 3 to 10-person startup, because this is where I see the most reckless AI code deployment happening right now. The reasoning is always the same. We're moving fast, we'll access later. We're not a big enough target for attackers. I've heard this exact sentence before incidents at companies that were 3 months from IPO. The startup roadmap is not about adding bureaucracy. It's about the 4 gates you can implement in a single sprint with 0 dedicated security resources. In week 1, you add detect secrets as a pre-commit hook across the whole team. 1 command, 30 minutes, done. You add a semgrep GitHub action to the main branch. 1 YAML file, 15 minutes. In week 2, you establish PR rule. Any AI-generated code must be tagged with a comment. This tells the reviewer to apply the H1 and H2 manual checks. In week 3, you add npm audit or pip audit to your CI and set it to fail on high severity CVEs. That's your minimum viable gate for a startup. 4 gates, 3 weeks, no new headcount. The 5th gate, test coverage enforcement, comes in sprint 2 when the team has stopped flinching at the first 4. The brutal truth. A startup that single credential leak or auth bypass from AI-generated code loses weeks of engineering time in the incident response alone. 3 weeks of setup versus weeks of cleanup. The math is obvious. What happens when your team grows past 10 people and you need to assign ownership to these gates? Mid-sized teams, roughly 20 to 100 people, face a completely different problem. The startup can operate on informal norms. Everyone knows who reviews what. At 50 people across 3 or 4 product teams, informal norms collapse. Code review becomes inconsistent. Some teams apply the checklist rigorously, others rubber stamp it. I've seen this fragmentation destroy the value of a perfectly designed gate system. The mid-size roadmap has one central principle. The tech lead owns the gate, not the team. A specific named human being is accountable for gate compliance in their domain. This is not about blame, it's about clarity. When nobody owns it, nobody enforces it. The 90-day rollout looks like this. In the first 30 days, you run a half-day training session, not a lecture, a workshop where developers actually apply the H1 and H2 checklists to real recent PRs and discover what they missed. This creates visceral understanding that no amount of slides can replace. Days 31 through 60, you roll out the automated gates team by team, starting with the highest risk team, usually the one touching payments, auth, or core data models. Days 61 through 90, you conduct a cross-team compliance audit, sample 10 AI-generated PRs from the past month and score them against the full checklist. The gap between what teams think they're doing and what the audit reveals is always humbling. And that humbling is exactly what makes the program stick. The question is, what happens when you scale this to an enterprise with compliance requirements and external SI vendors writing AI-generated code on your behalf? Enterprise implementation is a completely different beast. And I say that having survived multiple large-scale digital transformation projects in Korean chaebols and government-adjacent SI environments. The technical checklist is actually the easy part at enterprise scale. The hard part is threefold. First, compliance audit trails. In regulated industries, finance, healthcare, public sector, every AI-generated code merge needs a traceable record. What model generated it, what version, what prompt was used, who reviewed it, and what gate outputs were recorded. This has to be baked into your PR template and your CI artifact store from day one, because retrofitting it is a nightmare. Second, party and SI vendor AI code. This is the one that keeps me up at night. Your SI vendor is using Copilot or Cursor to write code they're handing off to you. They are almost certainly not running any of these gates. You need to contractually require gate compliance and technically enforce it by running your own gates against their deliverable before accepting it into your repository. Get this in the contract. I have seen enterprises accept entire SI deliverables that were 40% to AI generated, unreviewed, with 3 critical CVEs and 2 hard-coded staging credentials. And third, organizational change management. You cannot email a checklist to 500 developers and expect adoption. You need a champion network, 1 embedded advocate per business unit, and you need executive sponsorship that makes gate compliance a performance metric, not a suggestion. The payoff when all 3 are in place is significant. You get an AI code safety posture that actually scales. And everything we've just built in this section, all 3 roadmaps, only works if you avoid the anti-patterns we're about to expose. The next section might be the most important 5 minutes of this entire lecture. I want to spend time on this section because in all my years of watching teams adopt new engineering practices, the failure mode is almost never we didn't know what to do. It's we did the wrong version of the right thing. Here are the 5 anti-patterns that will make your entire AI code safety program worthless while giving you the dangerous illusion of safety. Anti-pattern 1. Using AI to review AI output. I see this constantly. Teams feed their Copilot-generated code into ChatGPT and ask, is this safe? And treat the answer as a gate pass. This is not a gate. 2 LLMs have overlapping blind spots. The hallucinations and emission patterns are correlated. You need static analysis tools and human domain experts, not a second opinion from a different AI. Anti-pattern 2. Checklist theater. The PDF is on the wall, the boxes get checked, but there's zero enforcement mechanism. Any checklist item that can be bypassed under deadline pressure will be bypassed under deadline pressure. Anti-pattern 3. One-time setup, never revisited. The SenGrep rules you configured 6 months ago don't cover the new attack patterns from last month. Static analysis rulesets need quarterly reviews. Anti-pattern 4. Applying the same review intensity to all AI-generated code regardless of risk surface. Not all code is equal. A UI component and a payment processing function need fundamentally different review depth. Anti-pattern 5. Treating a failed gate as a bureaucratic obstacle rather than a signal. When developers start learning how to make the gate pass without actually fixing the underlying issue, suppression comments, test coverage gaming, your program has already failed culturally. Each of these 5 patterns has a specific countermeasure. Let me show you what the healthy version looks like. Here's the uncomfortable truth that no tooling vendor will tell you. You can implement every single automated gate perfectly and still have AI-generated code disasters if your team culture doesn't support honest review. I've watched teams where the most senior developer merged AI-generated code with obvious issues because no junior engineer felt safe questioning them. The tool caught nothing because the tool was never consulted, the senior just pushed to main directly. Culture is not soft. Culture is the thing that determines whether your expensive security tooling actually runs. The behavioral practices I'm about to show you are what make the difference between a program that works in a demo and a program that works at 2 a.m. on a Friday when someone is under deadline pressure. First, normalize saying I don't trust this AI output. Make it expected behavior, not an exceptional act of courage. Second, establish the explicit team norm that questioning AI-generated code is a skill to be praised, not a sign of mistrust toward the developer who used the AI. Third, run monthly AI code review retrospectives. Pick one real AI-generated incident or near miss from the past month and review it as a team learning exercise, not a blame session. Fourth, make the gate bypass process deliberately uncomfortable. If someone needs to override a gate, it requires a written justification committed to the repository. Not an email. Not a Slack message. A permanent record in the codebase. This makes bypasses rare and deliberate rather than reflexive. And here's the bridge to where we're going next. The checklist, the roadmaps, the culture practices, they are only useful if you start implementing them. In the final chapter, we're going to give you one concrete action you can take before you finish work tomorrow. Not a roadmap. The one that produces the highest return in the least time. All right, no more theory. You've sat 5 chapters, patterns, gate models, and team size roadmaps. Now I'm going to give you the exact sequence of actions for the next 48 hours. Here's what I tell every tech lead who comes to me after a production incident caused by AI-generated code. The first move is never to build a big new process. The first move is to audit one thing you already have. Right now, in the next 2 hours, pull the last AI-assisted PR that got merged to main. Open it. Run through the 3-gate checklist we covered in Chapter 4. I promise you, in 80% of cases, you will find at least one item that was skipped. That single audit will do more to convince your team than any slide deck. By end of day today, install the minimum automated gate. I'm talking about one pre-commit hook, or one CI pipeline rule. Pick whichever is lowest friction for your stack. Even a single SenGrep rule targeting hard-coded secrets is better than nothing. And by day, run a 15-minute stand-up briefing. Not a 2-hour workshop. 15 minutes. Show the audit finding. Show the gate you installed. Ask one question. What would have happened if this reached production? That question changes the conversation faster than any mandate from above. The 48-hour plan is not about perfection, it's about establishing a beachhead. Because the team that starts imperfectly today will outrun the team waiting for the perfect rollout plan next quarter. But here's the part most teams miss entirely, and I'll show you exactly what it looks like in the next scene. Now, here's where most teams self-sabotage after a great start. They install the gates but never measure whether they're actually working. I've seen this exact pattern at 3 different enterprise clients. They build a beautiful checklist, run it for 2 months, and when the CTO asks, is AI code safer now? Nobody has a number. Let's fix that right now by defining the 3 metrics that actually matter. First, defect escape rate for AI-attributed code. This means tracking bugs found in production or staging that are traceable back to AI-generated commits. You need to tag these commits. Even a simple git commit message convention like AI-assisted is enough to start. Compare this rate against your baseline human-written code defect rate. If AI code is escaping at 2x the rate, your gates are not tight enough. Second, gate bypass frequency. Every time someone uses no verify to skip a pre-commit hook or manually overrides a CI check, that's a bypass event. Log it. Review it weekly. In healthy teams, bypass frequency drops over the first month as developers internalize the gates. If it's rising, you have a culture problem, not a tooling problem. Third, review cycle time impact. One of the most common objections I hear is the gates slow us down. Measure it. Add a timestamp at PR open and PR merge. If AI-assisted PRs with gates are taking more than % longer than pre-gate PRs, your gates are too heavy and need. The goal is safety without velocities. These 3 numbers together tell you everything. And the surprising truth, teams that instrument these metrics actually ship faster within 90 days. Because they stop chasing ghosts in production. The complete reference summary you'll want to screenshot is coming up right now. We've covered a lot of ground across 6 chapters. Let me give you the 1-slide summary, the screenshot mode. Here are the 5 failure patterns that kill AI code quality in production. Context collapse, where the AI lacks system-wide awareness. Silent hallucination, where confident wrong answers bypass review. Security pattern drift, where deprecated or vulnerable patterns get reproduced. Test coverage illusion, where AI writes tests that pass but don't protect. And ownership diffusion, where nobody feels accountable for AI-generated logic. Against those 5 patterns, we've built 3-stage gate model. Stage 1, pre-commit automated, secrets, static analysis, license check. Stage 2, logic and architecture review, the human checkpoint AI cannot replace. Stage 3, production observability, AI-specific anomaly, tagging in your monitoring stack. On top of Anthropic's official framework, we added 4 field-validated layers that their documentation won't tell you. The Korean SI multi-vendor accountability gap, the legacy API integration risk that AI models consistently underweight, the regulatory compliance check that can't be automated away, and the on-call knowledge transfer requirement so your midnight engineer can actually understand and own the AI code they're inheriting. And depending on your team size, solo developer, startup squad, or enterprise, we gave you a concrete deployment roadmap calibrated to your actual constraints. This is the complete system. Not a checklist to file and forget. A living process you iterate every sprint. The one thing I want you to walk away with: AI coding tools are genuinely powerful. But power without a verified safety layer is just a faster way to reach the same disasters we've been cleaning up for 25 years. Your team deserves both the speed and the safety. Now let me show you where to go next. You've now got the foundation. But I want to be honest with you, this lecture is the safety floor, not the ceiling. The teams that will truly master AI-assisted development are the ones who go deeper in 3 specific directions. First, AI-specific test strategy design. The way you write tests for AI-generated code is fundamentally different from testing human-written code. You need property-based testing, mutation testing calibrated to AI hallucination patterns, and contract tests that pin external API assumptions that AI models frequently get wrong. This is an entire discipline on its own. Second, model version change impact assessment. Every time your AI coding assistant updates its underlying model, your existing codebase faces a new risk profile. The suggestions change. The patterns change. We need systematic ways to detect when a model update has shifted the risk envelope of your AI-assisted workflow. Third, evaluating when to trust AI output by code category. Not all code is equal. Infrastructure as code, authentication flows, financial calculation logic, and UI string formatting carry completely different risk weights. Building a trust calibration matrix for your specific domain is the next level of maturity. These topics are where I'm taking this series next. If you've made it through all 6 chapters, you already have the mindset. You know the failure modes. You have the gates. Now it's time to go from mastery. Start with the 48-hour plan. Measure the 3 metrics. Then come back when you're ready to go deeper. The teams that combine AI speed with disciplined safety verification. Those are the teams that will still be shipping confidently 5 years from now, when everyone else is still fighting production fires. Go build something safe.